we're going to look at function notation, also known as functional notation, which is an extremely important notation for dealing with functions throughout mathematics. So function notation is a way of expressing a function. For example, we can have f of x equals something. Now, the f here is the name of the function, and the x is the argument. So we have the name of the function here, and we have the argument here. These parentheses are not multiplication, okay? They reserve a space to put in the input, the element of the domain that is getting transformed by this function. And then after the equal sign, we have something that shows us how to transform the inputs. In this example, we have that f of x equals 3x plus 1, which means that for any input to the argument, any element of the domain, we take that element and we multiply it by 3 and add 1 to get the output. And we can think of this as being like a machine. This machine has its instructions right here. The instructions are take the input, multiply by 3 and add 1, and then the output comes out the other side. So if I put in a 1 into the machine, the 1 comes along, the machine says, I know how to do this. I go 3 times 1 plus 1, that equals 4, and out goes a 4. If I put a 2 into the machine, the 2 comes along, the machine says, I know how to deal with a 2. I go 3 times 2 plus 1, that equals 7, and then a 7 comes out the other side, and so on. Over here, I have some inputs. Over here, I have some outputs. And if I were to map them, I could map 1 maps to 4, 2 maps to 7, and so on. And with this particular function, of course, my x could be anything. In other words, we would say that the domain is that x is in the set of all real numbers. And correspondingly, the range, y, is going to be the set of all real numbers because we know from our work with linear relations and linear functions that this relation here will cover every single member of the real number set in its outputs. Now, one thing to be aware of, we can also write a function like this, f x to 3x plus 1. It's an alternative notation. We'll mostly use the first notation, but you should be aware of this other way of writing it. Now, one of the advantages to function notation is that we have names to refer to when we have more than one function that we're dealing with. For example, I might have a particular situation where sometimes I need to square a number, sometimes I need to subtract 1 from it, and sometimes I need to multiply it by 4, and I can now refer to these different functions as f, g, and h. And I can in fact combine them, which is something we'll be doing later on. Note that each of the functions in blue is equivalent with each of the functions in green beside it. Let's do a few examples. Suppose we have g of 5. What does that equal? Well, we take the function g, and the function g says whatever your input is, you put that input right here and subtract off 1. So since I'm starting with 5, I would go 5 minus 1. My output for an input of 5 is 4. And if I wanted to put it in this form, I could say 5 comma 4. How about h of 7? Well, the input is 7. We go 4 times 7 and get 28. How about f of negative 3? Well, my input is negative 3. So the function says my input is being squared. So I would have to write negative 3, the entire input being squared, and negative 3 times negative 3 is positive 9. So for an input of negative 3, the function f gives me an output of positive 9. What about these? Here our inputs are no longer numbers, but they are expressions, variables or expressions of variables. Well, the same logic applies. If I have g of a, then that means that a is the input to the function g, and the function g says take your input and subtract 1. So my output would be a minus 1. It doesn't matter that it's not an actual number. It's okay to have an expression as my output. H of a plus 1. Well, h is 4 times the input, and the input is a plus 1. So I'd have 4 times the input. The input is a plus 1. Don't forget those brackets. So that's my output. That's fine. Or if I wanted to expand it, I could say I have 4a plus 4. F of 2x. Well, the input is x, which is 2x. Actually, that's a little confusing, isn't it? So my input here is 2x. The function says take your input, whatever it is, and square it. So what I would have to do here is take my input, 2x, and square it. It doesn't matter that we have the same variable name here as we have here. It's just a placeholder. Whatever this input is, we square it. I could change my function if it made me happier and say, oh, this is identical to f of w equals w squared. And now I don't have the variable conflict. 2x is my input, so I have a 2x squared. But normally we don't bother changing the letter for the function, and we're just comfortable with the fact that whatever the input is, even if it contains the same letter, that entire input is squared. So here we would get that f of 2x is 2x squared, which is 2x times 2x, or 4x squared. That's my output for that one. Now, of course, there's nothing stopping us with starting with an output and asking what the input had to be. H of x gives an output of 20. Solve for x. Figure out what the input would have had to be. And I can quite simply just replace this h of x with 4x, because that's what h of x is, and then perform basic algebra and see that x had to be 5. Then we can see, checking it out, that h of 5 means 4 times 5, which is indeed the output of 20, as expected. So we can go forwards or backwards with functions, doesn't matter. Now, of course, functions do not have to be provided to us as equations. They could be provided to us in ovals, they could be provided to us as a set of ordered pairs, they could be provided to us in graphical form. So here I have a function displayed, f of x, and you can see clearly that the horizontal axis is the input or the domain, x, and that the vertical axis is the output or the range, f of x. And I could be asked, for example, what is f of 3? Well, f of 3 means I have an input of 3 and an output of 1. So there it is. I could be asked, what is the value of x when f of x equals 2? Well, my output is 2, so my input was 6. So here I would say this implies that x equals 6. And we should now have enough understanding to do exercise 2b.